Hello guys, welcome to this new video. So here we are going to solve the first question in the May 25 Specimen Paper 2. So here we are told that a block of mass of 45 kilograms is on this horizontal table and we have no friction at this surface. And we have a 15 kilogram block on top of this big block, and this force F accelerates both blocks in such a way that these two blocks do not move relative to each other. And we are also told that the coefficient of static friction between the block and the object is 0.6. So at this surface we have a coefficient of static friction of 0.6. So firstly we need to state the nature and the direction of the force that accelerates the 15 kilogram object. Well, obviously we see that there are no forces here, so like we don't have a separate force accelerating the 15 kilogram object, yet it still moves together with this 45 kilogram block. And well, the only way this is possible if there's a frictional force. So we can say static friction, as this is what keeps the blocks from sliding on each other, and it's static because, well, they're not moving. If they would be moving, then it would be, the surface here between them would be moving, then it would be dynamic friction, but we just say static friction here. We can also say between the blocks, and then we still need to state the direction as well. And well, we need to remember that frictional forces always act in a direction opposite to the direction of the movement. If you imagine like a car traveling to the right, like this, then the frictional forces will be trying to slow it down. So if the velocity is to the right, the frictional force will oppose this direction. And this is also the case when we think about projectile motion or any types of motion. Frictional force always acts in the direction opposite to the velocity's direction, so in the direction we would move. And well, if we just try and use our imagination a little bit here, if we imagine that there would be no friction over here on this surface, and we just pull this 45 kilogram block, then maybe we can imagine that this block would want to slide to the left a little bit, as they would want to separate. But here, that's not the case, so they actually stick together. So if we see that the block would want to move to the left, then that means we need to have a frictional force in the opposing direction to this. So we will have a frictional force to the right, like this. So we can also say directed to the right. To the right. So this is what is going to keep the block on top of this big block. Otherwise they would slip. And then in part B, we need to determine the largest magnitude of this pulling force, such that these two objects do not move relative to each other. So, well, first of all, we know that here in this whole system, the only force acting is this F. So if we would want to write the Newton's second law equation, so the sum of the F forces in the x direction, for example, now, then we could just say that the F net, the F net is just equal to the force we have here, as this is the only force being exerted on the system as a whole. And well, this is just equal to mass times acceleration. And yes, well, our mass is 15 plus 45, so 60 kilograms, and we don't know our acceleration yet. So that's how we can express the magnitude of our force. And well, we can also express the magnitude of this frictional force, as if we remember there's going to be a normal force at the surface between the blocks, and you know that frictional force is equal to the coefficient of static or dynamic friction. Here static times the normal force will give us this frictional force. So we can say that the frictional force is equal to this times n. And well, we know the coefficient is 0.6, and we can also calculate the normal force, as that's just the mass of this object times by g. So times 15 times 9.81. So this is 88.2 newtons, like this. And here we need to somewhat separate these two objects. So if we just think about this object at the top of 15 kilograms, and if we just draw the free body diagram of this, Then, well, in the vertical directions, we will have obviously the weight force and the normal force, but those cancel each other out anyways, and we don't really care about the vertical direction at the moment, so I'll just only draw this frictional force. But we see that the only force acting in this direction, in this horizontal direction, is just the frictional force. So we can say that for the 15 kilogram object, the net force is going to be equal to the force of friction, as well, that's the only force we have, but that's also equal to its mass times its acceleration, as Newton's second law states. So 15 times acceleration. And well, what is the acceleration? Well, we can remember that the acceleration of the system is constant, as they do not move relative to each other. So that means if this top block accelerates with like 1 meters per second to the right, this bottom block must also accelerate with 1 meters per second to the right, as otherwise if they would have different accelerations, then they wouldn't be at the same position at the same time, which would mean that they would slip, but that cannot happen as they stated here. So we can rearrange this first equation over here. So we can see that the acceleration will just be F over 60. So that's going to be the acceleration of the small block as well, not only of the whole system. So what we can do now is, well, we can plug this acceleration quantity into here. And well, we know the frictional force, so this and this are obviously the same. We know that 15 times A is 88.2. So what we can say is that 15 times F over 60, which is the acceleration, is equal to 88.2. And well, if we rearrange this, then we will find that this is approximately 350 newtons. So this is the maximum force that we can pull this system with. And well, this was the first question in this specimen paper. It was quite brief, I think, only 2 questions. I hope I was able to help, and see you in the next question.